Hello Math 8 students, this is Utah Middle School Math Project 9.2f. Similarity continued, more with similarity. To get started, I had students discuss the definition of similarity, and they came up with two figures are similar if one can be obtained from the other through a sequence of translations, reflections, rotations, and or dilations. I added the or because it doesn't have to include all of them. It could just be translations and dilations. It could just be rotations and dilations. So it could be a sequence of any of these options. The next thing I had students discuss is how are similar and congruent related? Those definitions are very, very closely related. What is that main difference between them? Seth? Exactly. Similar has dilations that produce scaled copies. Congruent does not. One thing that I would like to point or draw your attention to, I need all eyes on the screen right now. The definition of congruent, we have stated a couple ways. We've said two figures are congruent if one can be obtained through the other through a sequence of translations, reflections, or rotations, but we've also defined it as through a sequence of rigid transformations. So one thing that I would like to draw your attention to now, one thing I want to make clear, all of last unit we use this word rigid transformations. The word rigid transformations refers to translations, reflections, and rotations. Rigid because they're strict. They keep all of the properties. Notice now dilations are not a rigid transformation. Rigid transformations will keep all of the properties. Dilations, yes, the angles, as we saw here, the angles are preserved, they stay the same, but the side lengths are scaled up or scaled down, and they are non-congruent figures. So dilations are a non-rigid transformation. Now, let's continue on to 9.2f. I do have some from OUR 826 in here as well, but this is mostly Utah Middle School Math Project 9.2f. So in this one, we're just practicing defining each of those rigid transformations, or I guess not rigid, all of the transformations. It will take one figure to the next to prove similarity. It says here, these triangles are indeed similar. You need to show that they are similar using that definition of similarity, which means we need to describe those sequence of transformations. So I'll do this first one with you. It doesn't say which one we need to start with. I'm going to start here just because this is the one that I have highlighted blue. Yours might be a little bit different if you've already worked ahead of me. But if I take triangle SRT, the first thing that I'm going to do is I'm going to translate it down 1, 2, 3, and to the left 1, 2, 3, 4. So I'm going to write that down. I translated it down 3 and to the left 4. Not right, left. Now that I have them in place here, I can see that I really probably want to do a rotation before I try and do a dilation. I want to get them to line up as much as possible. So I'm going to use N as my center of rotation, and I can see that I want it to rotate 90 degrees. This side that is going vertical, I want it to rotate 90 degrees counterclockwise so that it lands horizontal. So then I'm going to rotate 90 degrees counterclockwise. Around N. When I do that, it lands right here. And I can see it's set up very, very nicely for a dilation now. I can see that it's set up nicely for a dilation because M and this would have been T, they're collinear, intersecting here at N. L and what would have been S are collinear, intersecting back here at N. And so we can see that N also would be that center of dilation. So dilate using N as center. And scale factor, because we do need to define our dilations using a center and a scale factor. What would that scale factor need to be? Yeah, 1/2, because here I have a length of 4 and it's going to shrink down to a length of 2. So 4 multiplied by 1/2 is how I get to 2. So scale factor would be 1/2. Non-geometry software here. There we go. That's it. I have now proven that those two figures are similar using that sequence of transformations. I realize probably the thing that would make this better is telling me where I started. I didn't make that explicit, but I start with triangle SRT is translated down. So I know that I'm starting here and making all these moves to this triangle to get it to line up here with triangle LNM. Write a similarity statement for these two triangles. So we would start by saying triangle SRT is similar to triangle. Make sure that our points correspond to one another. So S is up here. When it was translated, rotated, and then dilated down, that is triangle or point L. R corresponds with N, so I'm going to list that next. And T corresponds with M, so I list that at the end. Triangle SRT is similar to triangle LNM. I'm going to let you guys work on this next one with your groups. I think once you do one, it's pretty clear how to do the other. So this is really just practice. 2 is going to be more practice, and then 3 is where we switch gears and we do something a little bit different. So just work on number 2 with your groups, and then we will do number 3 together with your groups. Number 2, ready, set, go. If I start here at quadrilateral RSTU, what sequence of transformations would I need to do? Luke, get me started. What did you do first? Okay, translate it down 1 and right 1. While that is true, after we do it this way, in fact, I'm going to clone the page now. I want to show that there's another way that we can do this. Let me clone. Okay, so translate down 1 and right 1. And even if you did this different, someone else give me the next step. What would we do now? Emery? Reflect across the y-axis. And now, hopefully that gives us some really good clues. What would we do now? I don't just multiply by 1/2. What is that really called? Fits. Keep going, because I can't just say dilate. I need all those pieces of information. So close. You're so close. Dilate by a scale factor of 1/2. X or S. But you're right, we need to include our center of dilation as well. So let me get caught up on all the things that we've said. We're going to start with quadrilateral RSTU. We translated it down 1 and right 1 unit. Then we did a reflection over the y-axis. And then we perform a dilation with scale factor 1/2. And center, what is the center? How can we find the center of this dilation? Sam? Yeah, since it is lined up, you can see that. For those who can't, draw a line that goes from R through X and just extend it. You can see it goes through the Z, just like S through W is going to come on back and go through Z. And U through Y is going to come on back and go through Z. And that confirms that Z would be that center of dilation. So center would be Z. Does that make sense, Fitz? Okay, let me show one other way that we could have done this in fewer steps. Dilations are not quite as obvious, not quite as intuitive. So I'm going to just show you another way that we could have done this. I'm going to reflect over the y-axis first. So that was 2 away, and now it is 2 away. I can do a dilation right now. No translation necessary. You might not see it in the very beginning as you're going through these, but do like I just did here, where I drew lines to go from those corresponding points to see where they all intersect. I'm going to do that same thing now. So this would be going from R through X, S through W, U through Y. What is that center of dilation? It's the origin, right? So I could have done that in fewer steps. The only thing that's different is I didn't need to do the translation. It still is scale factor 1/2, and I just changed that center. So I would just like to point out that we can sometimes avoid that translation if these are lined up to be perfectly aligned. Okay, even this one going back from T through what was that one? Whatever that point is, it's all covered up. These all go back through that origin. So that is another option. I'm going to list that one as well, just so that we can have that for our notes. Alternatively, we could have just reflected over the y-axis, and in fewer steps go straight to dilation. Dilate with scale factor 1/2. And center of dilation is the origin. Okay, now write a similarity statement. I actually have to come over here to write my similarity statement because my other one was too full. What is that similarity statement? Quadrilateral RSTU is similar to what? Don't make me do the work for you. RSTU is similar to Siley. W, X, Y, Z. Agree or disagree? I disagree. We need to make sure that we're paying attention to those corresponding points as well. So let's focus just on R. Where is R in the new figure? Here it is. And it would be X, exactly. So R is at the beginning, which means I need to list its corresponding point, which is X. Let's do one more together. S is the next one. Where is S in the new one? W. Siley, fix that for me then. X, W, finish it up. Not quite. ZY, yes. X, W, ZY. We need to make sure that we're paying attention to the order that they're listed in. Okay, next problem, number 3. This one is not saying that they are similar. It's saying determine if they are congruent or similar or neither and provide a justification. So if they are congruent, we should be able to tell pretty easily. Are these congruent? No. Are they similar? Can I go from one to the other using translations, reflections, rotations, and dilations? Give it a try. Use your tracing paper. Give it a try first, and then we can go over it together. Are these, we know for sure they're not congruent. That's easy to see. Are they similar, or are they none of the above? Check in with your groups. You're going to pause the recording. All right, are they similar? Just an open discussion. Are they similar? No. Now justify it. Tell me how you know they're not similar. Let's start with Sam. Okay. Good. Yeah. So I'm gonna address this just a tiny bit differently. What I want to see is we can easily count or measure the lengths of these straight pieces, right? It's a diagonal that we have a trouble with. So Sam wasn't even attempting to measure the diagonal. He was just saying, well, the diagonal is too wide and the diagonal is too wide. If this is a bigger figure, does it make sense that it would still be too wide in that diagonal in the same way that this is? So that's a great justification. Danielle. Okay, great. So using this, we can say the scale factor should be 2. Let's test out that scale factor in other places. Here we have a length of 6. 6 multiplied by 2 should give us a distance of 12, and instead this is a distance of 8. So we have an issue that scale factor is not consistent. Great justifications. Who has another justification? Emery?
I was trying to see if it was a dilation, so I drew all the points together and none of them met up in the same spot.
None of them met up in the same spot. And sometimes that happens if we need to do a translation first. But I still think that's a really good way to determine that. If I take this step and translate it first, now we should be able to still see these points lining up, and we can see they are not, right? They're not lining up. So sometimes we might want to confirm that by taking a step to translate it first, but that is still a really good thing. One more. Remember this property. If they're similar, I'm going to go back. If they're similar, angles should be the same. So that's another great way to do this. If I trace one of them with tracing paper, I can then move it over. Are those the same angles? No. Look at this. Black one goes to here. The blue one goes to here. Those are not going to be the same angles. So those are all great justifications. You write down the one that you like the best. Different scale factors. The diagonal didn't change its width. We can even say angle measures were not preserved. No matter how you decide to justify it, as long as you have one of those types of justifications, then I think it's safe to say that these are not similar, not congruent. These are neither. Okay, we worked together on that one. This next one I just want you to do on your own. I'll show the answer at the end, but I want you guys to work on this one on your own. Are these congruent, similar, or neither? Let's just start. Are they congruent? Yeah? They're congruent? Be careful. No, they're clearly not congruent because they're different sizes. Are they similar, or are they none of the above? That's what you're discussing with your groups. We're going to pause the recording as they discuss. All right, students in class, when they first started working on this, they said, yes, they're similar because they're the same shape. Is that how we prove that they're similar? Is that how we really properly justify? No. Well, how do we actually justify? Don't give me all of the specific details for this problem, but in general, how would we justify that, yes, they're similar? Gracie? Exactly. We would justify by listing the sequence of transformations that will take one to the other. And I think it's clear in this one of those transformations that we would have to use would have to include dilations. Who has a good justification? Who has a sequence of transformations? I was hoping, okay, I was going to say, I really liked what I saw over there. I'm curious to know if you guys are going to be willing to share. Is it Hayden? Peyton. Sorry, Peyton. Okay. The middle point? What do you mean by the middle point? How could we name this point? So you're describing this point. What do I call that point? There's a way we can name this point, and it's not just let's call it A. How can we describe this point that we're talking about? Seth? Yeah, give its position, write down the coordinates. So we would say 3, 2. Yes. So let's write down those things that were said. Even if you did it a different way, if you have extra space, you can say, or we can do such and such. So help me out. This was translate down 2 and write 3. Is that correct? Or did I get those backwards? Down 2 units and right 3 units. And then we reflected over the y-axis. So you all should be writing this down too. Like I said, even if you already found another way, it's good to have your eyes opened and to see another way that this could be done. Reflect over y-axis. And then we can dilate with scale factor 1/2. Sorry, is that better? And center, instead of just saying randomly the point that's in the middle, we can actually use the coordinates because it's on a grid. And so since it's on a grid, we can easily just name it using those grid points. If you also wanted to give it another name and call it A, you can do that. But I like using the grid center 3, 2. One more way that we can do this. Seth, will you tell me one more way that we could do this? So we're going to go straight to a reflection. Okay, so reflect over y-axis. Hold on 1 second, let me get that. So this is 6 away from the mirror, so when I reflect it, it's still going to be 6 away, so right here. Do I have it in the correct position? Looks like it. I'm just going to eyeball it. Okay, go ahead, continue. Good. How did you find that the center of dilation was going to be the origin? How did you do that? Yeah, we can see these corresponding points. When I extend those lines going through all of these corresponding points, we can see that in fewer steps, all of those go through that origin. So when I connect all of these corresponding points, they all intersect back here. So I know that we can, instead of having to worry about an additional transformation and translating it, we also could have gone straight to dilation. Scale factor is still 1/2. But now the center is the origin, or the point 0, 0. That's all that we're going to do in this video. We're going to continue this lesson another day. So thanks for watching, and we'll see you next time.